Welcome back to Physics 141 Online. Today I'd like to introduce the ideal gas law, which many of you have probably encountered in a previous course, maybe a high school chemistry course. Robert Boyle, who was an English scientist and a contemporary of Isaac Newton's, was the first one to discover that for all gases, the product of the pressure is a measure of the force per unit volume that a gas exerts on the walls of its container, and a volume V, that the product of P and V is approximately a constant for all gases as long as the temperature doesn't change. And so there was a little bit more detail that was gained from further experiments by two others, Charles and Gay-Lussac, and what they discovered was that the constant in Boyle's law is linearly proportional to the temperature if the temperature is expressed on an absolute scale, which we now know as the Kelvin scale. And so this gives a more general relationship that P times V is not only a constant, but it's a constant that depends on the value of the temperature. So if the temperature changes, then technically it's not a constant. But this C that is in front of the temperature is something that's a constant essentially for all gases. And it's easy to show that this constant depends on the size of the sample. And one way of quantifying the size of the sample is expressing it in terms of the number of molecules in the sample. And so with all of these experimental insights put together, the version of the ideal gas law, looking at it on the basis of the number of molecules in the sample, goes like this. The pressure times the volume is equal to the number of molecules times a constant that we now refer to as Boltzmann's constant multiplied by the absolute temperature in Kelvin. So N is the number of molecules, and Boltzmann's constant, in order for the units to work out right, must be expressed in units of energy per temperature, joules per Kelvin. And we can check on that because the left-hand side of the equation is force times volume over area. And a little bit of thinking will show you that that actually is an energy unit. So the left-hand side is joules, and the right-hand side is joules per Kelvin times temperature in Kelvin, so that's also joules. So this is the ideal gas law in terms of the number of molecules that you have in the gas sample. But there's another form that we use, and that takes into account the fact that for a macroscopic sample of gas, N is a huge number, something on the order of 10 to the 23 or even higher. And so what we usually do, rather than express the ideal gas law in terms of the number of molecules, we define the number of moles of that gas as the number of molecules divided by Avogadro's number. And that's probably a number that's familiar to you from previous classes. So we replace capital N with the product of little n, the number of moles, times Avogadro's number, right? So inserting that into the ideal gas law gives this expression. And so now we have the product of two constants, Avogadro's number times the Boltzmann constant, and the product of those two constants is itself a constant that we usually call the ideal gas constant, and we use capital R to denote that. So if you take Boltzmann's constant K sub B and Avogadro's number and multiply them out, you get a number that's just a little bit over 8 in terms of joules per mole Kelvin. So the final version of the ideal gas law that now is a little bit more convenient because it's expressed using the number of moles of sample is PV equals nRT. And another way of writing this down is to realize that if we take PV over T, that's equal to a constant for a particular gas if the number of moles of gas stays the same. And so this can be a very useful equation to use if you've got a gas that undergoes changes in either pressure or volume or temperature, or maybe all three, because we know that this quantity, PV over T, for a particular gas remains constant, so that if the volume goes up, either the pressure must go down or the temperature must go up in order to keep this quantity on the left-hand side equal to a constant. So you have some homework problems that will ask you to use the ideal gas law to calculate some of those kinds of changes in a gas property. Now, what about this whole notion that the ideal gas law really describes not just the behavior of one particular gas, but all gases. And it's really remarkable that experimental data show that in the limit of low pressures, where the interactions between gas molecules become so infrequent that we can basically neglect them, all gases display this kind of universal behavior. And so what this graph shows is a summary of experimental data. If we measure this quantity, pressure times volume, over the number of moles times the temperature for a particular gas, and if that gas has a pressure that varies, so this is plotting pressure in the unit of atmospheres, then it turns out that at very low pressures, all gases, although they follow their own individual curves on this graph, they all intersect. If we extrapolate down to zero pressure, they all intersect at the same point. And this point is the gas constant, because PV over NT is equal to R. And that's a really remarkable expression, but what it shows is that at the very, very lowest of pressures, where the gas is very dilute, that all gas molecules behave essentially the same. So even though when the pressure goes up, gas molecules can be distinguished from one another in the way they behave, they all follow this ideal behavior in the limit of low pressure. And so that kind of raises the question, why do gases show non-ideal behavior as their pressure increases? There's a couple of different reasons, but the simplest one I've already kind of alluded to, and that is that when gases are compressed to a higher pressure, then there's a greater likelihood of the gas molecules interacting with one another. The system becomes more dense, and so it turns out that gas molecules, when they get very, very close together, actually have an attractive interaction with one another, and that's going to change the way that they behave. Ideal gas behavior is basically expressing the assumption that gas molecules bounce off the walls of the container that they're trapped in, but that they don't interact very much with one another. And so that's going to be a good approximation for a dilute gas system, but if that gas system has its pressure increase so that the density changes, those interactions between gas molecules are going to become more frequent, and they do tend to change the properties of a gas. And so that's why at higher pressures we can see different behavior for different gases. There's a little bit more detail on this in your textbook, and you can read this for yourself. I hope this has been a helpful introduction, and I will see you in class.